Okay, let's get started. Microsegmentation made easy with OT SDN. OT SDN stands for Software-Defined Networking for Operational Technology Networks. My name is Thomas Walsen. I am a business development manager and product manager for OT cybersecurity solutions at HMS Networks. From heritage, I'm Dutch, but since 30 years back I've lived in Göteborg in Sweden. But the longer I live abroad, the more nationalistic I become. That's why I have an orange jacket, right? But more importantly, my background is in telecoms. I've worked with operational critical networks, telecom networks, for over 20 years. And then on top of that, 10 years focused on cybersecurity for OT networks. I think working with telecom has given me a great perspective, because in telecom, nowhere is it ever more important that the networks are always working. You can call 911 and your call should get through. At the same time, integrity is very much respected. If I call you, you trust that the caller ID is correct. And last but not least, every bit counts, because every bit is charged for. So that is also very, very important. And this type of background is very good to have when you move to other critical networks. HMS Networks, you might not have heard of us. We are a company founded in Sweden 35 years ago. We are experts at industrial protocols. So we make machines talk. And we do that under a few different brands, among others Anybus, E1, which is a Belgium from origin company, and Tron and Red Lion, building different type of solutions, facilitating communications, remote access, or switching technologies. The company is 1,100 people and turns over 400 million euros. It's quite large. So first of all, let's talk a little bit about what we are doing this for. There are three specific OT incidents that I want to bring forward, where I think we can learn from and realize why it is important that we care more about OT security. This one is largely under the radar. It was in Saudi Arabia in 2017. The specific attack towards the Triton Trisys Schneider Electric safety systems. When they analyzed the code there, it was really purposely built to try to trigger explosions. Now that didn't happen, thank God for all of us, because the programmers made critical errors in their code. But nonetheless, it became a significant event for the cybersecurity industry, because this really showed that there can be real criminal intent to cause harm. And it's very possible to compromise safety systems. So a good event to keep in mind. A second, of a totally different classification, shows how much impact cyber incidents can have. Colonial Pipeline, probably many have heard of this in the US, was actually an IT attack. It was the IT systems that got compromised, but for some reason the OT environment could not continue to function. This is something unthinkable in telecom. Well, if the billing system goes down, the prepaid system will still work. I mean, this is separated from each other. It's critical infrastructure, and that is completely failed in OT environments outside of the telecom space. And this is a good example of that. And a critical consequence was that different states could not get gas to the pumps, so it started to hurt American people. Couldn't drive their cars, right? That hurts. But a more significant consequence is that it has resulted in regulations. So the US has imposed regulations on the pipeline operators that they now must take cybersecurity seriously. And a third event is in Ukraine. Of course, a lot is happening in Ukraine. Russia is attacking all the time. But this particular event was the Russian adversaries utilizing common Modbus protocol to manipulate the building heating system. They actually broke into the network in April, but they waited until January, the year after, until they went in and manipulated the heating system so it shut down. And that is a testament to a big problem we have with industrial protocols, is that they are inherently insecure. So as soon as you have access to the network, you can manipulate things. And this is a wake-up call that shows that it can quite easily be done and have physical consequences as well. It was solved in a few days, thank God, but it just shows what can be possible. So, industrial security, a reality check. We need to start to understand, why are we so much at risk, right? And if we look in our own backyard, like I said, HMS has 35 years experience in building industrial networks. We have seen it all. We can see that things have changed quite a lot over the last few years. If we think way back, 10, 20 years back, networks would maybe be built like this. You have a PLC, you have some Ethernet connectivity, but at large, the operational network is built with serial connectivity. To hack this, you need to manipulate the PLC program and make changes. That's different for every company. It's quite difficult. There are successful examples of this. Most famous Stuxnet, right? The US government and Israeli government supposedly did that towards the Iranian enrichment facilities, reprogrammed the PLC so that the centrifuges span out of control irregularly and they broke down quicker. But they spent millions of dollars and approximately 4 or 5 years of preparation doing that one hack. There's not many other examples of where this will happen. So you could say that this was good security through obscurity for all the rest of us that are not a high profile target like that. The problem is, however, that networks are changing. 10 years ago, we released a protocol report, a report about the use of industrial protocols in the world. And 10 years ago, it looked approximately like this. What you have to remember here is that orange is serial networks and this is Ethernet-based networks. 10 years later, it looks like this. Here we have Ethernet-based networks and then some serial-based networks left. The summary of it all is that 10 years ago, 66% of new devices deployed were still serial. And today, 65% of the devices are Ethernet with an IP-based protocol. And then there's another set of Ethernet that are not IP-based, like EtherCAT, for instance. So networks have changed a lot in their technology. So now networks look like this. It's Ethernet underneath and Ethernet above. The PLC might still separate things if you keep yourself to Siemens guidelines, but the risk has definitely increased. To hack from above, you still need to hack the PLC, but to hack from underneath, as long as you have physical access or remote access or any way can reach the network here, you can manipulate and disturb the process quite easily, especially because networks here have started to use a lot of IT protocols as well. Networks like this, however, don't persist very long because they're locked in to a single vendor and that blocks innovation. So naturally, networks have opened up, third-party systems are connected to the network, and basically it's just to connect and log in from an IT system from other systems. And that's the danger that we have built up now. So when we go out and troubleshoot operational networks, we very often find networks like this. Big flat networks where every such island is another machine, maybe delivered by a third party, with old PLCs or Windows computers of old stature or whatever mix, you know. And it's open networks like this that anything can talk to anything without problems. And that is a big risk. I wouldn't even recommend anybody in IT to build networks this large. And in OT, of course, consequences are far greater. So why are these networks so dangerous? Let's analyze that a bit. And first, we do have to say that there's a big problem with the use of Windows in operational environments. I said I came from telecom. We had a golden rule always: never ever no Windows in operations. It's not a reliable platform to work with. But in other OT environments, it's used a lot. And you know, it's a great platform. It's easy to build applications for, but it's very hard to harden down and keep updated. You can't reboot your factory every patch Tuesday. It just doesn't work like that. However, Windows has shaped up a lot in the last few years. Let's be honest, it's a much better platform today than 10 years ago. The problem is that we don't use today's Windows. We use yesterday's. Because in OT we build system for long life. Many call it legacy, but in fact we actually design them to be supported a long time. So it's long life systems. And Windows is not a long life system. So this is a complete mismatch in technology. Next is insufficient access control. We still see so many situations where it's convenient to use shared passwords, one password for the whole group to use, or no password at all, because then you can quickly access the HMI and stuff like that. And that's of course very convenient for operations, but it's also very convenient for hackers to access and do things. We also know that products used in manufacturing, especially, are by design less secure than products for other industries. Orange Cyber Defense did a great research on this, where they sort of analyzed all the CVEs reported on products and then categorized them in different industries, and they concluded that products used in manufacturing had a higher severity score by 33% than products used in other industries. So by design we know that many products in industrial environments are less secure by design. And last but not least, the inherent protocols that are used in OT, they are completely open and insecure. Many have secure versions, but they are not used. And that means that when people get access to the network, they can quite easily manipulate the process. And that's a real risk. And then we have to remember that external hackers are not the only problem. There are many reasons that a network can have downtime. It can be misbehaving equipment and old components, faulty equipment doing strange things. It can be wrong configurations or an excess number of devices that causes trouble. Of course, there can be cable trouble, and there can be an insider threat as well. It's a little bit of a foul world in Europe, right? But a lot of it can be unintentional. The sort of oops factor. I configured a VLAN here, and all of a sudden it has impact over there. That can be a big problem. And of course, we do need to take external cyber attacks realistic, but and we need to take them serious. But we have to also acknowledge that downtime is probably caused by many other causes, and when we want to find a solution, we want to try to find something that benefits us for all these type of causes. So security should really have been embedded in the network. We can't have these open networks as IP was originally designed. So let's move towards the solution. The promise of segmentation. Like a wise hacker said, you know, if I can't reach it, I can't attack it. It's as simple as that, right? So we gotta put in segmentation to make sure that people cannot reach the equipment that we have put out there. And that's very simple, right? Of course, we have a firewall between the cloud and our office environment because we don't want to be reached by hackers. But the cloud firewall here has one really big job. It's also let everything through in that direction because the majority of the workers here, they actually work in the cloud, right? But that is not enough. Of course, we put defense in depth in place, separate OT from IT, and good practice will tell you that you should use a different type of border here than here to make sure that you don't have the same risk with vulnerabilities. But what I'm saying is that this is not enough. We need to make sure that we, inside these OT environments, compartmentalize the networks far further in order to reduce the risk from threats from within, threats from remote access, threats from visiting workers, and by just machines interacting each other. So the aim should be to have borders around machines or better, right? Borders around devices. And that's hard. But doing this will significantly reduce the risk and the impact of an incident. And this is exactly what the standards prescribe you to do as well. If you look at the absolute best practice for OT security, IEC 62443-3 is for systems, and requirement 5.1 is network segmentation. It literally states logically segment control systems from null control systems and segment critical control systems from other control systems. What does that mean? You have a video camera surveilling your process, you have a PLC separate from each other. You have a safety system, you have a drive separate from each other. That's what's needed. And if you move to the second level, it's very explicit that the communications between these zones must be adopting a deny by default, allow by exception approach. So you need to know what talks to who and with what, and only allow that and disallow any other type of communications. So segmentation, according to these requirements, requires conduits, and it requires you to control and monitor the traffic between the zones. Okay, so how do we do that then? How can you implement this? There are many different ways. We could air gap it, we could put diodes in place. Lots of challenges with that. If you still want to get some traffic out, you need to get very specific configurations to work. You can't access it to fix things remotely. So there are some challenges with that. That's why it's used quite seldom, only specific environments. We can do logical segmentation, like suggested, with VLANs. And VLANs are a pain because VLANs is a distributed distributed configuration. You have to go to every switch and implement what you want, and it's static, and it doesn't make any communication of any security for traffic between the VLANs. It just separates the VLANs from each other. You can have physical network segmentation with firewalls, and that's a great solution. But it's a lot of work to implement this in a brownfield environment because you're going to need to readdress and reconnect things. So therefore, there are lots of hurdles with implementing this. When you look at those traditional type of solutions, you have a network situation and you create these zones. Then you have good security between the zones going up, the so-called north-south communication. That's controlled. But what about east-west? What about between the devices? There's no security there. So therefore, there's always a balance. How many zones do I need, and how large can I make each zone? And that is a difficult trade-off to make. The rules will be static. It's complex to manage. And in a brownfield installation, it's a bloody pain to implement because you probably need to readdress everything. So what to do? What about using orchestrated segmentation? This is where SDN networking comes in, software-defined networking. So what is software-defined networking? Software-defined networking is security embedded inside the network, not bolted on afterwards. And it comes from the telecom world. Many years ago, they wanted to separate the switching layer from the control layer, so that you control your traffic somewhere else and your infrastructure is somewhere else. Next, it's policy driven, and it has a deny by default rule set. It's that you need to explicitly allow what you want to allow, otherwise the network is not functioning. And then we have a solution that's designed for industrial needs, built with redundancy, because that's built into the protocol, and agile in the sense that you can move things around without a problem, plus OT device identification. So a little technology road here. How does this work? You build your network with switches. They look like layer 2 switches. They are like layer 2 managed switches, but they support SDN. And these are Anibus switches, but they can be Cisco or others that support SDN. It's an open standard, so there are many different solutions here. OpenFlow compatible switches are required. You connect them and they talk to a controller, which is a software run on top that can run on an industrial PC or on a virtualized layer. As soon as something is connected to the network, the network is asking for permission from the controller, and the controller will then decide that, okay, this PLC is identified in this way. It will be allowed to talk to that robot, but only on the traffic, only with traffic on port 44818, which is SIP Ethernet IP traffic, nothing else. So there's a path created for that, and it's locked down to that. Nothing else will work. If it needs to do more, it needs to have another policy. For instance, it might send OPC UA to the HMI. Well, then there will be traffic allowed on port 4840 to the HMI as well. So it's like putting a firewall on every port for every unique device that's connected to the network. A very good thing is that the policies are decided in the controller, but they're implemented in the switches. So the switches are not dependent on the controller for operations at all. But they do inform the central controller about what it's doing. So for the first time, you actually get from the layer 2 network information about who talks to who with what kind of protocol and how many bytes. When a visiting worker connects to the network, it will get denied, or it will be put into an isolation zone, whatever you decide in the controller. It can't just take over a port. Even if I move the PLC and put it on another port, the PLC will be reprogrammed, but the port will not be accessible for anybody else. And last but not least, if you want to copy out something, let's say that this specific path is interesting for us to monitor, then I can copy that traffic to a third-party device. So I can always have security log information as well. And last but not least, there's resiliency built into the network. So if this cross-connect would actually die, the network will automatically find the next best path for the traffic to reach its destination and be rerouted instantly. No more spanning tree, no more trouble. So that's SDN networking. Microsegmentation for every device, dynamic security policies, real-time visibility, a smart monitoring feed, and compatibility with any OpenFlow switch. So you can use Anybus or third-party switches. This is what it looks like in a GUI. So what you do here is that you would select 2 of the nodes that are automatically detected, and then it will draw up the traffic path that traffic is taken. And on the side here, it shows you what are the rules that are allowed for this traffic path and what's the observed traffic, what's actually happening on this traffic path. For the first time, you get visibility about your network, and it's drawn up automatically. So, OT SDN, simplified networking, maximum control. It eliminates complexity. There's no more VLAN handling. There's no more spanning tree problems. It's vendor independent. You can use our switches or any of the switches here or any others that are SDN compatible, which is many. And it is denied by default as per policy that is required. Really putting security embedded inside the network, not bolting it on afterwards. And it is excellent for brownfield networks because you can take old switches that are open and you can put a new switch in there. And what you can do with the software is put it in learning mode. So it will pass through, it will look like a switch still, but it will record all the traffic that's happening, create the rules, and then you can say, now I want to apply these rules, and then no other traffic paths will be established. So it's an excellent path for brownfield networks. You don't have to change out your network all at once. You can also work with hybrid deployment options. So in this little bit more complex picture, we switched out the distribution layer to an SDN switch. Here is a critical zone. There we also have an SDN switch. Here we have legacy networks and a couple of more legacy networks. The way this now works is that any traffic that goes through the SDN, no matter if it's direct connected, will require specific policies. So here it will have policies for traffic between these 2 devices as well. Here it will not have traffic policies for traffic between these 2, but it will have traffic policies for anything that goes up and back or up and to something else from any of the devices down here. Individual policies, not port policies. So that's really a conclusion. Who is this really for? This solution is excellent for asset owners of critical infrastructure and manufacturing where downtime is really problematic. Think about logistics centers, think about baggage handling systems, think about manufacturing that has to go on around the clock, places where downtime is really critical. And also where you don't have control of who has access to the networks. So think about an energy provider that has lots of substations that have physical security, but no eyes on it, that can be compromised. Somebody can go in there and plug something in. That's not possible anymore with the SDN network. So for those type of situations, it's perfect. It fits all industrial networks. It's working independently. It fits Profinet networks, fits Ethercat networks, it fits even IP, etc. And it really adds this east-west security that is basically impossible before. And when would you do it? Well, it's of course in a greenfield installation, it's perfect to start with SDN, but SDN is especially suitable for brownfield installations where it's impossible to create zones after an operational system is put in process, but you can easily swap up the switches, learn what's happening, and then enforce the policy afterwards. So OT SDN delivering east-west security, full visibility and control. That's both practical, scalable, and future ready. Great. Any questions? I'll be happy to answer them. We are just around the corner here with a little booth and a demo as well. So come by and talk to us and click through the interface yourself if you want to see and experience what an SDN network looks like and can be. Thank you very much.